Welcome to the deep dive. Today we're cutting through the complexity around generative AI. You see these powerful systems everywhere, right? Chatbots, translation tools. They feel, well, a bit like magic sometimes.
They really do. It's impressive stuff.
But what's the actual, the core innovation behind them? What's the breakthrough that really powers this whole revolution?
That breakthrough, the real game changer, is the transformer model. It landed and completely redefined how machines handle sequences, especially language. A totally radical departure.
Right, and that's exactly what we're doing in this deep dive. We're going to unpack that key paper, Attention is All You Need, and related sources, show you how the transformer works, why it was such a big deal, and the problems it actually solved.
Yeah, the goal is to give you a solid handle on this pivotal tech, kind of shortcut your way to really understanding it.
Okay, so to really get why the transformer was so brilliant, we probably need to look back first.
Yeah.
What came before?
Good point. For a long time, sequence models were mostly recurrent neural networks, RNNs.
RNNs, right. How do they work? I remember something about steps.
Exactly. Think of it like processing input one piece at a time. Word 1 comes in, the RNN does something, produces an output, and crucially, passes along a sort of memory, a hidden state.
Yeah.
Then word 2 comes in, combines with that hidden state, produces its output, updates the hidden state, and so on. Down the line for every single word. Inherently sequential, one after another.
Ah, I see, like a chain reaction.
Precisely. And while that was clever for its time, it had some pretty major drawbacks, limitations that really paved the way for the transformer.
Such as?
Well, first off, they were slow. Really slow for long sequences. Because each step depended on the one before it, you couldn't just process everything at once.
No parallel processing?
None. If you had 1,000 words, you had to do 1,000 steps in order. Made training on long text incredibly inefficient. Took forever.
Okay, so speed and scaling were issues because of that sequential nature. Makes sense.
Definitely. A major bottleneck. Then there was the second big problem, vanishing or exploding gradients.
Right, I've heard of that. It affects training.
Hugely.
Yeah.
During training, the network adjusts its internal weights, right? Think of the math like a long chain of multiplications. If the numbers getting multiplied are small, less than 1, the signal, the gradient, can shrink down to almost nothing. It vanishes.
So the model stops learning.
Pretty much, yeah. Especially for the earlier parts of the network. Or the opposite could happen. If the numbers are large, the gradient can just explode, get massive.
Which makes things unstable.
Totally unstable. Training can just crash. It's this really delicate balance.
Wow. It's kind of wild that these numerical issues could just paralyze the whole system.
It really highlights how sensitive deep learning can be.
Yeah.
And this vanishing gradient thing, it connects directly to the third, maybe the biggest problem, difficulty with long-range information. Because that signal got weaker and weaker down the chain, information from the beginning of a long sentence. It just got lost by the end. But think about human language. The subject of a sentence, mentioned hundreds of words ago, can still be crucial for understanding the verb right now. RNNs just couldn't reliably bridge those long gaps. The context faded.
Okay, so slow, unstable training and couldn't handle long-range context well. That sets the stage nicely.
Exactly.
So then the transformer arrives, and it tackles these problems by doing something pretty radical, right? Getting rid of recurrence altogether.
Completely. Dispensing with recurrence and convolutions entirely. No more step-by-step. No more hidden states trying to cram everything in. A huge leap.
So how does it work then, at a high level?
Well, you can think of the architecture as having two main parts, two big blocks. There's the encoder block, which takes in the input sequence like an English sentence. And then there's the decoder block, which generates the output sequence, maybe the Italian translation.
And they talk to each other.
They do. Information flows from the encoder to the decoder. And right at the end of the decoder, there's a final linear layer. Its job is to take the decoder's output and turn it into probabilities for every word in the dictionary. Helps it pick the next word.
Okay, the core structure.
Yeah.
But the real magic, the heart of it, is this attention mechanism, right?
Absolutely. That's the breakthrough.
What is attention, just basically?
At its core, it's a way for the network to focus, to dynamically weigh the importance of different parts of the input sequence when processing a particular word, like a spotlight that highlights what's most relevant right now.
Instead of just looking at everything equally or just the immediate neighbors.
Exactly. And the specific type used in the transformer is called self-attention.
Self-attention. Okay, how does that work?
The core idea involves representing your input sentence in 3 ways, using 3 matrices: query, key, and value. Q, K, and V.
QKV. Any easy analogy for that?
Yeah, think of it like looking something up. The query Q is what you're searching for, maybe the context needed for the current word. The keys, K, are like the labels or identifiers for all the words in the sentence. And the values, V, are the actual information, the content associated with each key.
Okay, Q is the question, K are the labels, V is the info.
Yeah.
So how does it calculate relevance with those?
It uses something called scaled dot product attention. It sounds complicated, but the calculation is quite elegant. You multiply the query matrix, Q, by the transpose of the key matrix, K transpose.
Right.
This Q times K transpose gives you scores, basically how much each word relates to every other word. These scores can get big, though, so you scale them down. You divide by the square root of the dimension of the keys, dk, usually 64 per head.
Why scale them?
Super important for stable training. Stops the gradients getting too big or too small later on, keeps things in a good range.
Right. Makes sense. Then what?
Then you apply a softmax function that turns all those scores into probabilities, basically. It makes them all add up to 1. So you get a distribution showing how relevant each word is.
Like a weighting.
Exactly. And finally, you multiply that probability matrix by the value matrix, V.
And the result of all that matrix math is?
You get a new representation for each word in your sentence. It's a matrix the same size as the input, but now each word's embedding, its vector, isn't just about the word itself. It's enriched. It captures its meaning, its position, and its relationship with all the other words in the sentence, weighted by relevance.
So it builds this dynamic map of connections across the whole sentence in one go.
Precisely. A very context-rich representation. And a couple of key things about this. It's permutation invariant, meaning shuffling the input shuffles the output, but the relationships learned for each word stay consistent internally. Also, that core calculation, no learned parameters right there.
Really? Where's the learning then?
The learning comes from the initial word embeddings and linear layers that create the Q, K, and V matrices and process the output later. And one more neat trick for the decoder, if you set certain scores to -infinity before the softmax.
They become 0 afterwards.
Exactly. Which lets you mask out future words the decoder shouldn't be allowed to see yet. Very important for generating text step by step.
Okay, that's really clever. So a single attention calculation gives this rich context.
Yeah.
But the paper talks about multi-head attention. Why more than one head?
Yeah, this is where it gets really interesting. Think of it like having multiple perspectives.
Okay.
A single word can have different roles, right? Like making could be a verb or part of a noun phrase. Or think of the word bank, riverbank, money bank. Different heads can learn to focus on different types of relationships simultaneously.
So one head might track grammar, another might track meaning.
Something like that. One might look at subject-verb agreement, another might see how adjectives modify nouns, another might link pronouns to what they refer to way back in the sentence. The paper's visualizations show this beautifully different heads lighting up different connections. It allows for a much more nuanced understanding.
So it's like getting multiple specialized views instead of just one general one. How does that work technically? Do you just run the attention multiple times?
Sort of, but more efficiently. Instead of doing one big attention calculation using the full model dimension, say 512,
Right.
you first linearly project the Q, K, and V matrices multiple times. Let's say 8 times for H8 heads, like in the base model.
Okay.
Each projection creates smaller Q, K, and V matrices. The dimension gets divided by the number of heads, so 512 divided by 8 gives you 64 for each head.
Right, smaller dimensions.
Then you calculate the scaled dot product attention for each of these 8 sets of smaller matrices in parallel.
Parallel processing again.
Exactly. Then you take the 8 output matrices from these heads, concatenate them back together, and do one final linear projection to get back to the original 512 dimension.
So you split the problem, solve the pieces in parallel with different perspectives, and then combine the insights.
That's a great way to put it, combining diverse insights into a single, richer representation.
Okay, so this powerful multi-head attention, how is it actually used inside the transformer? Are there different places it pops up?
Yes, there are 3 main ways it's used. First, inside the encoder, we have encoder self-attention. Here, each word can look at all the other words in the previous encoder layer. It's all about the encoder understanding the input sentence deeply.
Makes sense. Building internal context. What's second?
Second is in the decoder. It's called decoder masked self-attention. Similar idea. Each word looks back at previous words in the decoder, including itself, but it's masked.
The minus infinity trick again.
Exactly. It prevents the decoder from cheating by looking ahead at words it hasn't generated yet. Keeps the prediction causal. You only use what you've seen so far.
Crucial for generation. Okay, and the third?
The third links the two parts. It's encoder-decoder attention, sometimes called cross-attention. Here, the queries come from the decoder layer just below it.
Okay.
But the keys and values come from the final output of the encoder. This is how the decoder pays attention to the entire input sentence when deciding what word to generate next. It connects the source to the target.
Got it. So self-attention within the encoder, masked self-attention within the decoder, and cross-attention connecting decoder to encoder.
You got it. Those are the three key attention spots. But attention isn't the only piece, of course. There are other crucial components.
Right. What else is needed to make it all work?
Well, first you need input and output embeddings. We touched on this. Basically turning words or word pieces, tokens, into numerical vectors, usually dimension 512 in the base model.
And these vectors are learned?
Yes, very much so. They start somewhat randomly, but during training, the model adjusts them to capture the meaning and usage of words based on how they appear in the data. They're learned parameters.
Okay, fundamental starting point. Then what?
Then there's positional encoding. This is really clever. Since the transformer has no recurrence, no step-by-step processing, it doesn't inherently know the order of words. Is dog bites man the same as man bites dog? Obviously not.
Right. Order is critical in language. How did they solve that without recurrence?
They add information about the position directly to the word embeddings. They use a set of fixed sine and cosine functions with different frequencies. Based on the word's position, first word, second word, etc., a unique positional vector is generated and just added to the word's embedding.
Added, not learned.
Not learned. It's a fixed calculation, computed once, reused. It gives the model signals about both absolute position, where a word is, and relative position, how far apart words are. Surprisingly effective.
Huh. Fascinating that a fixed function works so well. Okay, embeddings, positional encoding. What else?
Next up is add and norm. You see, after each main sublayer, like after the attention mechanism and after the feed-forward network, it combines two things. First is a residual connection. You simply take the input to the sublayer and add it to the output of the sublayer. So it's output, input, plus sublayer input.
Why add the input back in?
It creates a shortcut. Helps the gradients flow backwards during training much more easily, straight through the addition. Really helps combat the vanishing gradient problem in deep networks.
Ah, okay. A direct path for the learning signal. And the norm part.
That's layer normalization. After the addition, you normalize the resulting vector. Importantly, it normalizes across the features for each individual example in the batch independently.
Unlike batch norm, which normalizes across the batch.
Exactly. Layer norm helps stabilize the training dynamics, making things less sensitive to the scale of inputs and weights inside the network. Helps address something called internal covariate shift. Basically, keeps the numbers in a nice range for easier learning.
So add a norm helps gradients flow and keeps training stable. Got it. Anything else?
Just one more main piece. The position-wise feed-forward networks. These are actually pretty simple. Inside each encoder and decoder layer, after the attention and add and norm, the output for each position is passed through its own identical, small, fully connected feed-forward network.
Independently for each word position.
Yep. Usually 2 linear layers with a ReLU activation in between. It adds more computational depth and nonlinearity, allowing the model to process the attention output further for each word.
Okay, so those are the main building blocks. Attention, embeddings, positional encoding, add and norm, feed-forward nets. Quite a few pieces.
It is, but they fit together very elegantly.
So putting it all together, what does this mean for actually using the model? How does it learn, and then how does it, say, translate something?
Right. The training process is where the parallel power really comes into play. Let's stick with English to Italian translation.
Yep.
During training, you feed the entire English input sentence into the encoder all at once. Simultaneously, you feed the entire target Italian sentence into the decoder, but it's shifted right.
Shifted right. What does that mean?
It means the decoder input starts with a special start of sentence token, and then word 1 of the target, then word 2, and so on. The decoder's job at each position is to predict the next word in the actual target sentence.
Ah, okay. So it sees start and predicts word 1, sees start word 1, and predicts word 2.
Well, during training, it actually gets the whole shifted target sequence at once. And because of the masking and the decoder's self-attention.
You can only look backwards.
Exactly. So even though it gets the whole sequence when predicting the word for position I, it can only use the input word up to I1. But the key is the whole input and the whole shifted output go through the network in one single forward pass.
One-time step. Unlike the RNN needing step after step.
Precisely. That's the huge advantage. O1, sequential operations, versus ON for RNNs. This massive parallelization is why transformers could train so much faster on the hardware available then, like GPUs.
Wow. And how does it learn from that?
It compares its prediction at each position, the probabilities from that final linear layer, with the actual next word in the target sentence. It calculates a loss, typically cross-entropy loss, measuring the difference. Then it uses back propagation to adjust all the weights in the embeddings, the attention mechanisms, the feed-forward networks, to reduce that loss.
And it does this over millions of sentence pairs.
Exactly. The original paper used the WMT 2014 English-German dataset, about 4.5 million pairs. The base model trained in about 12 hours on 8 P100 GPUs. The big model took 3.5 days. Pretty quick for the time, given the scale.
That parallel training really is the key for scale. Okay, so that's training. What about after it's trained? I want to translate a new sentence. Is that also all at once?
Good question. No, inference using the model is a bit different. It becomes sequential again, but only on the decoder side.
How so?
The encoder still processes your new input sentence, say, I love you very much, all in one go. Its output, representing the input sentence, is ready. But the decoder starts with just the start of sentence token. It uses that, plus the encoder output via cross-attention, to predict the first word. Let's say it predicts te.
Right.
Now, for the next step, the decoder takes start of sentence plus te as its input. It runs that through, again looking at the encoder output, and predicts the next word, maybe amo.
It feeds its own output back in as input for the next step.
Exactly. It's autoregressive. It keeps going. Input, start te amo, predict molto. It continues generating token by token until it predicts a special end of sentence token.
So inference is step-by-step generation, even though training was parallel.
Correct. Though each step itself is still very fast. And there are strategies here, too. You could just take the single most probable word at each step. That's called greedy search.
Okay.
Or you could use something like beam search, where you keep track of several top possibilities at each step. Exploring multiple potential sequences usually gives better results.
Got it. Training is parallel, inference is autoregressive, step-by-step on the output side.
You've nailed it.
So let's recap the impact. The transformer throws out recurrence and convolutions, uses attention. What were the immediate tangible wins? Why was everyone so excited?
The advantages were pretty clear, pretty quickly. First, just superior quality. On machine translation, the task it was designed for, it blew past the previous state-of-the-art models.
You have the scores.
Yeah, the paper reported BLU scores, that's a standard metric for translation quality, higher is better. For English to German, the big model hit 28.4. For English to French, 41.8. These were significant jumps, even beating previous ensemble models.
So, better results. What else?
Second, as we discussed, faster training and parallelization. This was huge, dramatically reduced training time and cost because it could leverage parallel hardware like GPUs so much more effectively than RNNs. That O1 versus ON sequential operations thing was a massive practical win.
Yeah, that seems critical for scaling up.
Absolutely. Third, better long-range dependencies, because attention allows any word to directly connect to any other word with a constant path length, regardless of distance.
Unlike the diminishing signal in RNNs.
Exactly. The transformer was just much, much better at capturing relationships between words far apart in a sentence or document, critical for real language understanding.
Okay, better quality, faster training, handles long context. Anything else? Was it just for translation?
No, that's another key point, generalizability. They showed it worked really well on other tasks, too, like English constituency parsing, analyzing sentence structure. It wasn't just a one-trick pony for translation. It was a powerful general sequence processing architecture.
Versatile.
Very. And finally, maybe a bit more subtle, but still important, interpretability. Those attention heads, you can visualize them. You can see which words the model is focusing on when processing another word.
The spotlight.
Right. And you can see different heads learning different things, some focusing on syntax, some on semantics. It offered a little window into the model's reasoning that was harder to get with RNNs.
So, better, faster, better context handling, more versatile, and even a bit more interpretable. No wonder it took off.
Yeah, it really ticked all the boxes. Yeah, and looking bigger picture, the transformer didn't just, solve some existing problems better. It gave us a fundamentally new, highly parallel way for models to think about sequences, especially language. That core idea that maybe attention is all you need, or at least the most crucial part, that directly paved the way for the huge language models, the LLMs that are everywhere today. It really set the course for modern AI.
It's incredible how one core architectural shift had such cascading effects. So the next time you're using some amazing generative AI, maybe just pause and think. If attention is the key to unlocking this level of understanding and creation, what other complex problems could be tackled by simply rethinking how we focus, how systems interact with information? Maybe the most powerful insights come not just from more data or more compute, but from learning where to pay attention.